Alright, this is the last time I'm going to be doing this with backprop and everything. So first I'm just going to say we need some struct to hold data. And the important thing is that if you're trying to, and this is the main objective of neural networks, or really any of these things that are being optimized using derivatives, using calculus, is that you need some way to compute the derivatives. You need some way to track that. And there are two ways really that this is typically done: forward mode differentiation, which I'm not going over, and reverse mode. And I forget there are some algorithmic reasons why reverse mode for large, I forget what it is. It has to do with the vector Jacobian product of the Jacob, I forget. In any case, what we're going to be doing is called reverse mode automatic differentiation. So reverse mode meaning we're going to build up a computational graph, and then we are going to backpropagate derivatives by applying the chain rule locally and recursively through a computational graph. And what I mean by a computational graph is, let's say that we have okay, so let's say that we have this computational graph here. Oh. Okay, so we have two floating point numbers, and then we have their product, and then we add one of them to the product. So this ends up being AB plus A, which is also equal to A times B plus 1. And if we were to manually differentiate this, DD, DA, we would get B plus 1, right? DD, DB should be A. Okay, so this will be equal to minus 1, and this will be equal to 3.5. So our goal here is to automatically do this. And we're going to do that pretty simply, actually. So what is it that we need? First, we need some way to store the actual value, because D is going to be equal to minus 7 plus 3.5 equal to minus 3.5. So we need some way to get this information, because we don't only want the gradient, we also want the final product, or the final result. So we're just going to call this X, and that's just going to be a float 64. Okay, then we also want this gradient information. I'm just going to call this dx. Actually, let's stick to x and grad. I'll call it data and grad. Apparently that's more in line with PyTorch or something. Okay, but then what do we need if we're going to recurse through this computational graph? And there's a name for this called a directed acyclic graph. Then we're going to need to store the previous nodes. So this is going to be a vec of node. And then finally, we want to store an op. Basically, whether or not, not just the nodes that were here, but also the plus. So prev would be C, A, and then op would be plus. And what we're going to do is we're not going to store a string or anything, but we're going to actually store an enum. And I'm only going to support two operations here. And this is going to be an op. Okay, great. But then it turns out that when we do this backpropagation, we want to mutate the nodes, but we're going to need multiple shared references to the nodes. And the way that you do this in Rust is by using reference counting. And so reference counting, we're gonna wrap node in a reference counted struct that also allows us to do runtime mutability. That's like a bunch of mumbo jumbo, but it's pretty simple. once you start to use it. So struct, I'm gonna call this a val, and the val is gonna store a node, and the node is a reference counted RefCell. Oh, I have to do RC RefCell node. Okay, and then here now we store not previous nodes. We're not owning the node does not own the other nodes. Now, if you had strictly a tree-shaped structure, that would actually be fine. But because we have potentially a computational graph where the out degree of every node is greater than 1, then you need to actually store these vec of val. Okay, cool. So now I'm just going to implement some methods on the val. And so the first one I'm going to implement is just function new. And this is going to take data, and that's a float 64, and it's going to return a self. A self, when you in Rust, when you have an impl something, self refers to the something. So so I can just do val RC new RefCell new node, and then I believe that this is going to be data grad 0 prev will just be an empty vec, and the op will be, oh, and we need one more op, which is a leaf, which means it has no, it's not the result of any, it's a leaf node of the computational graph. And so this is going to be a leaf. Okay. And so I just need to say op like that. And I think here I just need to say node is this. Okay, cool. So now I should be able to do this. And one thing I want to do probably is watch exec here. And maybe I'll do this in another thing so that I don't whatever. Okay, so let's just keep it here. That's fine. So where's the error? The error is indentation. I think I just need, oh, there we go. Okay, in any case, now I should be able to wrap a piece of data. So I should be able to do value, val, new, 3.5. So I should be able to do let a equal this. And now here, this is just our graph for reference, but we want to use this. Okay. B is going to be equal to val new minus 2. Let C equal, okay, so now here's where we get to a problem, right? Is what's going to happen here is cannot add val to val. We need to implement add on it, okay? So the way that you do this in Rust, and it's just kind of, it's not even that interesting in any sense. We're going to do impl add for, and then we're actually going to take a reference to it so it doesn't consume it. Okay, and the way that this is going to work is we're going to first have to give it a type output, and the type of the output is going to be a value. So, and one thing that I could do here is I could also, and this is implicit, is I could do this. That would be fine. But we don't need to do that because it implicitly does that. So now we just need to implement the add function itself, and remember again, self is going to be a reference to val. And so what we want to do here is why is this called value? I must have written that because I'm used to the old one. And one thing that we need to do here is we want to create a new val, right? But this function is just for basically a leaf node. So I'm actually going to write another one called from prev. And what this is going to do is this is going to take basically self is the left-hand side of the plus and right-hand side is the right-hand side of the plus. And I'm basically going to allow, this is kind of a more drawn out, and prev will be a vec of val. And we don't need the gradient because the gradient will be initialized to 0. But we need the op. So we need an op. And this will return a self. So this is just another way of creating values. But what it's going to do is basically this. The only thing that's new is that here we can just do this. And now we can rewrite this to call from prev vec empty vec op leaf. All right, so now we kind of refactored this, and I keep writing value, and I'm gonna keep doing that. Okay, so now what I can do is instead of calling new, which won't give me the access to the args that I want, I can just call val. Oh, can't I do this? Okay, you can't. I'm wondering. I guess maybe that's because self is a reference. I don't know. In any case, val from prev. Oh. And then the data is going to be self dot node dot and so the node, this is a node, right? So when I do this, I get access to that. And what I want to do is I want to borrow it. And then I want to get the data. But here, I'm going to be writing this so much that I'm going to implement some helper functions, that basically accessor functions. So function data is just going to take a reference to self and return an F64. And it'll just be self.node borrow.data. And then function grad. And we're just, templating this out. It's all boilerplate. It's not interesting at all. Okay, so now we have ways to do this. And I think the problem here is that we actually need to implement, we have to do this, because enums, you want to copy them. When they return, it's an owned value. And I'm pretty sure if we go to F64, it probably derives copy. I don't know that for sure, but that's what I would assume. So I do derive copy. And the problem here is that, oh wait, wrong place. Okay, good. So now we have data, grad, and op. And the point that I'm trying to make here, it's so easy to get lost in the weeds with this simple code, but it's like so simple. All I'm trying to do is I'm trying to say, when I add two values, I'm going to make a new value that stores the result of the mathematical operation in the data field. I'm going to do nothing to the gradient because the gradient will be computed later when we actually decide to do backpropagation. And then the previous will just store whichever values were used to generate this new value. All right, I'm not even going to draw the graphs because it's like, I did that already and it's boring. All right, so I'm just going to do self.data plus right-hand side dot data. And then prev will just be a vec of self and right-hand side. But the problem here is there's probably an ownership issue. So wait, if I do this and... Oh, you know what it is? We have a reference. And if I try to dereference... And what if I try to dereference this one? I guess that's fine. Okay, and then here op is going to be an add, because this is the plus operation. And then let's see here, where's the problem here? Cannot move out of self, which is behind a shared reference. Move occurs. Okay, so we don't want to copy. What we want to do is we want to clone. And this will give us another owned shared reference. I'm almost positive about this. Val does not implement clone. Where's my quick fix? So okay, so now cannot add val to val, but that's only because we have to dereference. But now that we've dereferenced, this works, and we can now print C. And this will fail because we did not implement debug. So now we got to go up here and add debug. And the problem is that node now does not implement debug. So we will just put that there. And then op needs to implement debug. And we're now good to go. And so now I can run this code. And we have literally a computational graph. So now, oh, but I wanted to do A times B. So what happened to A times B? Cannot multiply vals together. Okay. So now all I have to do is impl mul for reference to val. Okay, so the type, again, is just a val. And we need to implement the mul function. And this is literally the exact same code. So I can just do this. Except this is a times, and this is a mul. That's it. So there we go. And now I basically have my full computational graph. There we go. So this stores a graph that we can look at. And you know what? I guess I will do this. So this is some code that I actually didn't write. You can't copy this? What the hell? I need to ask, how do you just copy a file to the clipboard? I don't actually know how to do that. All right. Okay, so I should. All right, so this code now, there's a bunch of stuff on implementing value, and it allows us to just draw a graph viz thing. And here we see one thing that we need to do. That is impl op function symbol. And this gives us basically a way to render this enum to a string. So it's just going to take a self and it's going to return a string. I don't know if it returns a string or I don't know. But we're going to match on self and then op leaf goes to, oh wait, I think I want to do this. I want to do a static string that we can build just directly into the binary, because these are all static strings, so we can just we don't even have to worry about string lifetimes. So I think we do this, and then we do op add goes to plus, and op null goes to times. Okay, cool. So now we just need to change this to be val, and I think that's all good. Okay, cool. So now I should be able to actually do or val draw dot. How do I actually do it? So it looks like I'm going to call render graph on right dot. So it's probably like render graph. Did I I'd have to go back. Oh, here we go. Oh, you when it's a module, you have to do this. You have to do dot render graph. And does this render graph? This does everything, right? This just, yeah, okay. All right, and then this is the file name. Okay, I got it. All right, so this is just going to be D, but it's probably going to be a reference to D. And this is going to be graph. And that needs to be a reference, and yeah. All right, so here, and let's just do unwrap it. So then we're just gonna print okay, and now I should have this path. Okay, and here we go. We finally have a way to render the graphs. I mean, big whoop. Maybe I'll keep this here. So one thing that I can do is, let's say, let D equal, or let O equal D times D. Okay, so now we're just gonna, O is for output, so I never am changing that. I can use a bunch of letters. And there we go. Okay, so what's next? We need to start taking derivatives. And the way we're going to take derivatives is with backpropagation. So let me just write a helper function called setGrad that takes a self and doesn't return anything, but it does do self.node.borrowMute dot Oh, and it needs and so now I have this function called setGrad. And so one thing if I wanted to do, let's just go back to this. Okay, so this is our simpler thing. And so what I want to say is let o.setGrad of 1.0. Okay, so now we have the gradient 1 here. And what I want to do, and let's start with a simpler graph. Okay, so we have a simpler graph which is just a plus, and this is going to be easy. So if I have, let's just manually derive the derivative. So what do we have? The output is equal to a plus b. So then dO dA is equal to 1, and dO dB equals 1 as well. So we now know that that when we have a plus node, that we can propagate the derivatives are equal to 1. So what I'm going to write is a function called local back. So this is going to be called function local backward. And it's going to take a self, and it's not going to return anything, but it is going to mutate. And so what we do here in this function is we're going to do one step of the chain rule. So we're going to assume that self.grad is correct. And then apply the chain rule for prev. So and I don't know, do I need to clone this? I'm not sure if I need to clone this yet. So we just did the op, right? So what we're going to do here is, now let's say that I had a smaller graph, a different graph. Okay. So one thing that you may think is the appropriate thing to do is just say prev dot for each p, or let's call it n for node, or v for val. Okay, yeah, that's right. Then v dot set grad is 1. Okay, but what you need to remember is that this would be wrong. And the reason that that is wrong is, let's say that we had the graph a plus b, c equals a plus b, and then d is equal to 5c. Okay, so then dd dc is equal to 5. But then dc and let's do this. So this means that we're going to have 5 times a plus b, which is equal to 5a plus 5b. So then clearly you can see that dd dA is equal to 5 is equal to dd dB, right? So the appropriate thing to do is not just set it equal to 1, but let it equal to the parent node's gradient times 1. So this needs to be g times 1. Okay, Now let's do the example of mul. And mul, we should assert that, I think this is impossible, but I'm going to add this in. I didn't add this in before, but we assume that there's only 2. I wonder if the compiler can actually now allow me to say prev 0. Because presumably once I've asserted that this is exactly length, then I don't have to unwrap anything. I forget what to do on leaf, but okay, so now let's assume that our graph is, so this is the local back on an op add. And here let's do an op mul. So what we're going to have is C is equal to AB, and then D is equal to 5C. So then D is equal to 5AB. So DD DA is equal to 5B, and DD DB is equal to 5A. So locally we see that, you know, DD DC is equal to 5. And then DC DA, or let's do, yeah, DA is equal to B. So then by the chain rule, we see that DD DA by the product is equal to 5B. So that's enough, and now we know what to do. So basically we can say left-hand side dot set grad, and this gradient is going to be G times right-hand side dot data, because data is what we're calling the B. So here G is self.grad, and that self.grad is going to be 5 because that's the output, the DD divided by DC. So that's the 5. And so we need to multiply the 5 times the local derivative of the left-hand side, which is A is the left-hand side. So DCDA is equal to B, which is B is right-hand side dot data. So did we do that? Is that what I did? Right-hand side dot data. And so now I can say our right-hand side dot set grad is equal to G times left-hand side dot data. And so now I'm not quite done. If we have a leaf, no, there's nothing to do. There's nothing to do. Because look, you have no previous, so there's nothing. You already assume that self.grad is correct. So, yeah. So I need to clone these to make a new references to them so that I can use them. I think. I don't know. I might just clone a bunch because cloning is cheap because it's an RC, so it doesn't actually matter. So we finally implemented what I think is probably the most important function to write if you're trying to understand backprop. I would say that. Maybe self.back, but local backwards is, like, to me, the crux, because this is where you apply the chain rule from calculus. That's like the main mathematical piece of understanding is how is it, given a computational DAG, how can I do one step of the recursion? Okay, cool. So now what we want to do is we want to actually fill in all this data. And I'm going to go back to this being C. So now we have this more complicated graph. And I'll expose what is a pretty serious bug in both of these branches. Okay, so what I'm going to do is manually do backpropagation. So we're going to start with the end here. So we already set, oh, and one thing to note, okay, imagine we have O. What is DO, DO? It's 1. So D's, and O is D. So then the derivative of something with respect to itself is 1. So we've seeded the reverse pass. So now we're going to start to do O.local backwards. Okay, so we've now taken this plus node, and the derivative of this is D, C, A, and B. So the derivative, what did we calculate? The derivative where's our full expression? D is equal to C plus A, so then dd dc is equal to 1. So that's appropriate. And then the derivative dA is 1 here. Now that's not right because it's supposed to be -1. But let's proceed with the algorithm. So now we need to do dc dA and dc dB. So what I'm going to do now is call C.local backwards. And we're going to get that the derivative is -2. dA, so this gave us that dc dd dA is equal to -2, which is wrong. And dd dB is equal to 3.5. And that one ends up being actually correct. But why is this wrong? And I'll explain why. The reason it's wrong is because we actually have to accumulate these gradients. We don't just set it to this value, but we have to do v dot grad plus. And same for here. We want to accumulate. And we now have the appropriate gradients. So we want to accumulate. And one way to think about it is you have to sum all of the paths from the output node to any given node. All right, so we basically have manual backpropagation. But now there's an important piece of, okay, we don't want to there's some internal structure that we implicitly said, okay, well, we had to do this order O first and then C first. And so the idea there is that we need to do what's called topological sorting. And it's a fancy ass name. And let's see if I can actually remember the algorithm, because it's been basically what we're going to do is we're going to start at the end. Okay. I think I got it. So we're going to do a function called build topo, which is going to take a v, which is a value, or a val. And it's going to return a vec of val. And what this function does is it returns a topologically unsorted list of the values of the DAG. Okay, that's a bunch of fancy words. But now I need to stub a function called visit, which is going to take a val. It's going to take a visited list. Visited. And this is going to be a weird type. It's a hash set of usize. I'm pretty sure it's a usize. Basically, what this hack is, and I'll get to it, is we treat, I think, the location, we treat the pointer. Okay, so values are RCs, right? They're reference counted. So we can take the reference counted and get the pointer itself. And the pointer is a usize. It's a, whatever, it's a pointer. And we can use that pointer as node identity. So like if we want to know if two nodes are the same, we look at their place in memory. And that's how we determine whether or not a node is the same. And so that is just how we're going to keep track of whether a node has been visited is based on whether or not we visited a node in the past with the same pointer. And then finally, we want our topo, which is just going to be the list. And this is just going to be a vec of val. And presumably, we need to change these types to not be owned, but mutable references. And same with this is probably a mutable reference. And this is not actually going to do anything return-wise. So its output type is nothing. So here's what we're going to do. We are first going to make then we're going to say visit v. And then we need to provide it visited and topo. And why is this all complaining to me? Oh yeah, because I need to make this let mute reference. But I think I actually have to explicitly say that I'm giving out this mutable reference. And yes, that's exactly right. Okay, cool. So now this is going to recurse on itself. It's going to call itself. But it's going to progressively build up visited and topo. So then all I'm going to do is call topo.revert. Well, actually, I'm not going to do that yet. That's stupid. I'm just going to return topo. All right, so now this compiles, I think, because this is a no-op function. So what we're going to do is if we haven't visited.contains v dot as pointer, or do I have to do this? If it doesn't contain it, then what we're going to call is visited.insert I'm just going to extract this out. This is going to be called let v pointer, or pointer v, so the pointer of v. Then if it contains pointer v, and what's wrong here? Oh, because I think I have to do. No. I'm not sure. This doesn't seem right. I might have to check my other code on topo sort. Oh, okay, yeah. All right, so this is correct. The only thing is that we need to cast it as a usize. But a better way to write this, and I'm going to hide my old code. Let pointer v equal self, or wait, v dot note dot as pointer as usize, and that's it. And that's a cleaner way to write it, in my opinion. Okay. Okay, I can reference it. That's fine. Then we're going to insert pointer v. Okay, now what I want to do is call visit on each of the children. So I'm going to do, and I think, I don't mutate it, so I can probably call self.node.borrow.prev, and then I probably have to call .clone because this is so now I can call it v.prev.forEach. And this is going to be for each value. I'm going to call visit on v. Oh wait, this is going to be. It needs to be a different name. Okay, cool. So now I'm mapping. I'm visiting all of the other ones, and then finally, once I've visited those, only after. So. I'm not doing a good job of explaining this, but the idea is that that if I want to compute the gradient of this node, I'm going to have to, before anything else, compute the gradient of its parents. So here, I want to compute this gradient first and then this gradient, and only after those two will I compute this gradient. And that's the idea. Let me double check that. Okay, yeah, I feel like I did a proper job explaining. So now all I need to do is finally, once I've visited all of the children, only then will I do topo.append. Append takes a vec. Push. Topo.push v. Do I need to clone it? Okay, and then finally, visit doesn't need to return anything. Only topo returns something. So now that we've determined, build topo has determined the order in which we can do this manual process where we called local backwards. So now, but the thing is, if you look at this, what will be the very last element of topo? It will be v, right? Because we push only after we visit the children. So we actually need to reverse this, so we start here and then go backwards. So what we're going to do is write backwards. So we're going to call function backward. Backward? I think it's backward. And it's going to take a self. And it's going to return nothing. It's just going to populate, it's going to populate the DAG. And so we're going to first do self.setGrad to 1.0. Then we're going to build topo of self dot reverse dot, oh, this is actually annoying. Is there not a function that, like, okay, whatever. So okay, now what we can do is topo is a vec of val, and we can do dot for each val v dot local backwards. And I think that's it. And so now if I turn this off and I turn these two off, we now have zeros all around the board, but I can do o dot backward now. And we have our gradients. So we've just done backpropagation, which is probably the most fundamental, I would say, like thing to do is backpropagation. But we're not really at a neural network yet. So I'll commit this. So backprop is done. And there's probably some bugs, but I actually don't know if there's any bugs. Because we did this properly. There may be one or two, but it's not a big deal. Well, okay, wait. Okay. Take a 2-minute break. Down, 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 down. Down, 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 down. Okay, but the important part is now neural networks. So neural network is just basically and what we're going to implement is a thing called an MLP, and multi-layer perceptron. So first I'm just going to do struct neuron. And a neuron, I think the picture is actually a good thing to do. Oh. Okay, wait, I have to wait for chat to finish. I asked, is there any bugs? It's going to tell me if there's bugs. Oh. All right, so it's right. Bye. Pray for me. Yeah, I am. Oh, yeah, okay. So, alright. So this is just going to, the comment disappears if you edit the code. That's kind of interesting. Huh. Okay, what is it that I'm trying to say here? Let's just look up. No, okay. The function of a perceptron. Okay, so let's say you have a neuron and okay. Oh. Yeah, good luck. Okay. All right. So yeah, so we have a weight okay. You have a neuron. And the neuron has inputs, which are basically other neurons. And the neuron will learn how to weight each of its predecessors. Make sure I'm not getting a call. Okay, and it will then apply, okay, whatever. The function is, let's just say it's tanh, hard code deactivation, tanh of dot of x and self.w plus self.b. But what I'm trying to figure out is that this is a scalar output. One thing I want to check actually is off by one error. Okay, yeah, so I should do that. That's what I want. I didn't want to get an off by 1 error. Okay, so we've initialized the weight vector, and now we want the bias to be the exact same thing, just this. And so, yeah, we'll walk through forward pass. Oh, and what I want to do actually is I want to make this a trait. And this matches PyTorch apparently. I don't even use PyTorch that much, but we're going to have a trait, and it's called module. And the trait requires you to implement a function called forward, which should take a self and an x, which is a vec of val, and it will return a vec of val. And I think that's all you have to do to define traits, right? Is there anything else? Okay, and then we need a function called back. We don't need backward because backward's implemented. Wait, do we? No, I don't think so. Okay, so let me then just try to do the forward part. This is the part that I'm not as... Okay, so what do we need? We need forward. And so what we're going to do is we're going to take the, this was the function that we're trying to implement, right? So it's going to be tanh, and we'll see how tanh comes about as being an issue in a moment. Oh wait, who is both dereference both dereferences? Oh dude, I didn't even see you. Dude, this guy Shorts World YouTube is okay, wait, hold on. I got a bunch of chats that I want to read actually. On stream to see if we can figure out what this guy's talking about, because it's actually pretty interesting. It's clearly someone that's actually engaged. Let's see, what is it that he's writing? Mute. Okay. So let's see if I can do this. Let's close this. We don't need the DAG anymore, and we don't need this sidebar. Okay. So here's what I want to see. Dereference both references before. Wait, is this like a bot? Loki, this looks like a bot wrote this. Like, what? I feel like this is a bot, dude. It's like running OCR on it. That's so weird. Anyways, let's continue. Okay. So we're trying to implement this tan h of the dot product of x and w. So we need this x. So what we're gonna do is self.w. Maybe I should do this. Assert eq. I don't know. This is 2 O of n passes. I don't think I mean, what a real library would do is like tensor sizes are probably part of the type or something. I don't know. But self.w.len and x.len. Okay, so we're going to do self.w.zip x dot wait, why is xi? I forgot about this type, man. This type is confusing. I mean, wi is a vec of val. Is it though? Let's just do it the easy way. For okay, so oh, interesting. They have a trait for add a sign. Okay, wait, well, can't I do... No? But then, okay, wait, but here, now I want to do vec of res.tanh. And then this will be, say, we can't find tanh. So now we have to do an impl tanh. So tanh, right? tanh, just like the pluses and everything, is an operation that produces a new value. So it's actually going to be self new, but it's going to be from prev. And the data is going to be self.data.tanh, which is so this is the F64, so then tanh is implemented on F64. Now this is going to be self.clone, right? And then the op is going to be a new op called tanh. So here now we have to do tanh. But then here we've now missing a, and this is the beauty of pattern matching, is that instantly it's like, oh, here's all these places where you need to continue work. Like, you're not done just because you implemented one of them. So I love Rust. And so here, this is the last one. This is super important. And actually, I want to put this up here. And then op tanh. We need to understand how to propagate the derivatives to the previous. So, I mean, most of this, if not all of this, is all copied from Andre's video. But, is it, wait, why am I... Anyways, in here, there's a section for the derivatives. So the derivative of tanh is 1 minus tanh squared of x. So all right, that's fine. But the derivative is going to be self g times 1 minus I think that's right. But this is not right, because we need to also say okay, so we have the tanh now, and then all we have to do is dereference this, and then the annoying thing is we probably have to then dereference this. Cannot multiply, oh, because this is already, okay. Cannot add val to val, so then we have to do this, this, and this. A little bit nasty, but that's okay. Okay, cool. So Now I'm just going to quickly check what the answer was for the neuron forward. Also, one thing that needs to be changed is, see here that this is a 0. Typically, you actually randomly initialize, I think. Oh, okay, wait, hold on. So here's how you could do that in a fold. You would do self.w.zip x.map, and then the map would be a tuple of wi xi, and you'd do wi times reference xi. That'll give you a value. Okay, then we do dot fold. Okay, and the init would be self.bias. And we might have to clone this. And then here, this is going to take the sum, the rolling sum and the product. And basically, it's going to store the result of this function in the sum. So we're going to then roll in the sum. So we're going to take sum plus prod. Okay, and then finally, I think we just need to do dot tanh. And then dot .2vec, can we do that? I think we just need it. So this is a val, so we just need to wrap it in a vec. And then here we just got to clone this. Okay, so that's the like fancy way to do it. On every forward pass, we're going to assert this length. I don't think so, buddy. I'm just going to assume that it's right. Okay, now we're going to implement layer. So layer is just going to be okay. So layer is just going to be a vec of neurons. So the number of inputs is going to be a U size, or U size, or a U64. Well, let's just do U64. And then the outputs, and this returns a self. And then this is just going to be, and it's just going to be All right, so there we go. Now we have a layer. But now the problem is layer needs to impl module. So what do we need? We need forward. So So all we need to do is self.neurons dot flat map n dot forward x dot collect. Okay, I mean that's pretty simple, right? So for each neuron, we are going to call forward on the input. And so this is a dot product, then the next one dot product, and so we're going to be doing n number of neuron number of dot products. And so one thing that I want to test actually is just quickly, let's pull back up the graph.svg. And what I want to do is let O is equal to d.tanh. And I just want to see if we can see. Oh, we're not compiling yet. We need to fix some stuff. So here we have a tanh. Okay, good. And so now a multi-layer perceptron is basically just now we're just doing yet another struct. And here is just going to be layers, and it's going to be a vec layer. And that's it. And we just need to impl MLP function new. And here it's going to take the n in. Which is a U64. And then a vec of n outs. And this will be a self, and this needs to be a vec of U64. And so basically what we're going to do is so let's just say that we had a vec of sizes. So V is like the sizes of, then we would do layer. Okay, yeah, so wait, hold on, I got this. So So what we're doing here is we're iterating over the length of the. So first we insert n in into n out, just so that we have all of the layer sizes kind of one after another, and that's what we do. Now we're going over the index, and what we're going to do is basically call layer new n outs of index, n outs of index plus 1. And then I think we just have to call dot collect. Oh. And that's it, almost. Oh, because MLP layers like this. There we go. And this, we'll just say it's immutable back. Wait, how do I do it? Oh, I see. Okay. I don't think that's exactly how I did it last time. I think I probably gave this as a reference to immutable vec, but like who really cares? Okay, so that's pretty cool. So now I'm just gonna copy all of this stuff as the old main. So this is the old main, and I'm just gonna move this to like a junk folder. Okay. So let's just make a. Oh, this was a function that I actually want to try to write myself. Okay, so I want to write a function called values that takes an into iterator where t is equal to into f64. That's what I want to do. And then it returns a vec of value. That's what I want to do. So function values where into f64. Okay, so that compiles. So now it's going to take x's, which is an into iterator where item is equal to t. Right? Is that there's something. Oh, I think you have to say x is impl into iterator. Bam. And actually, do I even have to do this? Can I just do this? Am I allowed to do this? Or wait, impl. Can I put impl here too? Oh, that's so cool. That's so cool, dude. What a beautiful piece of code. So now I should be able to say x's dot map x value new x or val new x dot collect. Oh, and I forgot to. So now I should be able to say Okay. So that worked. So now the values function. So I should be able to just print the values. Oh yeah. Man, this function alone is like such a good explanation of how Rust is so freaking expressive. Okay, so what am I trying to do? I'm trying to make an MLP now. MLP new. Oh, did I ever? I don't think I actually did something that's quite important, which was impl module for MLP. So here what I need to do is let mute O. I think. Maybe I have to clone it. I probably have to clone this. And then what I can do is for L in self.layers, O is equal to L dot forward of O. And then return the O. I think I just have to dereference it. Cool. All right, so now that I have implemented the forward pass for the MLP, we can now construct the multi-layer perceptron, and we're gonna, let's say that it starts with 3 inputs, and then the layer sizes are going to be a vec of 4, 4, and 1. So there's 1 output. I think I need to make this mutable if I'm going to change them, or no. I actually can't remember. I don't think I do. Okay, so now what I want to do is I want to call mlp.forward on x's. And what I want to do is actually, I only want to take the, so wait, let's do this. Assert eq out.len 1. I just want to see, okay, cool. So then let O equal out 0 dot clone, I think. And then what I want to do is the draw dot thing. So now I want to do this. Okay, so now we have a neural network, and we can actually look at the computational graph of the neural network. And so this is what it is. And it's just a bunch of adds, moles, and a single tanh at the end. Or wait, actually no, there's intermediate tanh somewhere. So these are all tanh. So that's the layer boundary. So all these tanh, that's the layer boundary. So 1, 2, 3. Okay, so it's time now to get to loss function and gradient descent. So okay, so let's I'm going to copy my data set from the okay, I'm going to copy this data set. Okay, so we're going to initialize our network. Oh, and one thing that I probably wanted to do, actually, before I do this, all right, we're going to look at the computational graph again, except here I forgot to do O.backward. Now we look at this, and the problem is since the data is all 0, our gradients are junk here. They go to 0. The gradients go to 0, which is... okay, so what I want to do here is now one small update, which is randomly initialize the weights and biases of the neurons to be... so I think I have to do cargo add rand. And then I have to do... Instead of this, I want to do random range minus 1 dot 1 dot. And I'm going to do that same thing for the bias. All right, so now every time we initialize this network, it's going to be different. And so now, if we look at the graph, you can see there's all sorts of data in here, and the gradients are all filled in with numbers of some sort. So that's pretty neat, actually, I think. Pretty cool. So, okay, now it's time to implement the loss function. So the whole idea of neural networks is that I should be able to do compute some... I have a data set, and I'm trying to approximate, you know, given an input that's similar to the data set's input, you know, predict what its output would be in a general case, not just on the training set example or on the data set examples. And so what I'm going to do is MLP or x's.map. Can I do that on a slice directly? Yeah, so we're going to do map for each x MLP.forward of x. And so now we have our predictions, and we probably have to collect. Or actually, what is the resulting type of this? Let pred y prediction. So these are, so our network eventually is going to be trying to predict these values given these as input. And so yes, we have a slice here. So that's pretty cool. And so now what I'm going to do is wise.zip ypred.map ypred. Okay. And it's going to be I know how to do this, I think. Y minus y. Oh, I think I can just do this. So, oh, we probably need to implement the power rule. We need to add let's just call the values on this. So ypred, oh yeah, I want to do this. So ypred, the MLP has an output size of 1. So this, even though it's returning a vec each time, it's just kind of a quirk of the sizes. So we're actually going to just do this. Oh, but sub is not implemented. Do you see this? Sub is not implemented. So what we have to do now is go back to our traits, and we're going to do impl sub for val, and type, oh, and this is just going to be self plus minus 1.0 times right hand side. Okay, but then cannot multiply this. So I think I'm just gonna do this. I know last time I actually went through and last time I also did this, impl add F64 for val, and I did all of that. But it's like, do you really want to do, like, do I really want to do all that? So this, then this, and this. Okay, so there we go. Now we have sub. So we iterate, we zip, we map. Now we have this. But now we have this value, and we want to do pow I, pow 2. And so this, we now need to do another one of these things where we have function pow, self, and then I think I-64, right? Okay, so this is kind of the same as before, right? Is we it's going to be a little bit interesting because it's going to be .pow I exp, and this might error out because yeah, it needs to be an I32 for some reason. I'm not sure why. And then this is right, and then this needs to be pow. But the interesting thing here. Okay, so we'll get to why this ends up being weird, but so let's just do it as before, and now we have to do the derivative. And the problem is though that here's the problem. We could have pow's prev so okay, here's the point that I'm trying to make. This could be a val, right? A reference to a val, but then it would be a child, right? Then we put the exponent here, but then we have to compute the, you know, if we have x to the y, x to the power of y, then we have to compute, and that, let's say that's z equals x to the power of y. Then we have to do dz dx and dz dy, and you know, maybe we just say that's not implemented for right now. And I think that that's just kind of like a later thing. So the way to get around this is we leave this as an I32. Okay. We keep that. But now here in op, we are actually going to parameterize this based on the exponent. And so that's going to be an I32. But then we need to change this to be an owned string, which means that every time we draw the thing, it's going to need to, you know, write this out and copy out this data. But I'm like so fine with that. This should be X. Oh wait, I need to write format. And I think I don't even need this toString. I think this is a no op. That format returns a string. Oh man. Okay, so now I just need to make that. The op now stores this exponent so that we only, now the last step and the most important step is the local derivative. So derive more. What is derive more? Bob, dude, we should play some Factorio. Actually, I'm like, I need to take a nap, but I really want to play some Factorio. Derive more, create. What is that? Ooh, this looks cool. But I don't think that this would help. Because I still definitely need to implement the derivative part. Or the, I don't know. I'm sure that there is a way to compress it a little bit. But what do I want to do? So I assume. Okay, so we assume that there's going to be only one child because the way that we constructed the only place where POW nodes, there's only one child, and so I'm gonna do this. So this is kind of the template for unary ops. So we have the child, and its gradient is going to be its own gradient plus g times, and then now this is the tan specific part. And what we want is it's going to be if I have, let's say, x to the 3, and I take the derivative, so y is equal to x to the 3, then dy dx will be 3x squared. So so if I have x to the z is equal to x to the y, then dz dx will be y times x to the power of y minus 1. So it should be exp. I think I need to do val. Okay, wait. Let me do it here. It's going to be val new exp reference dot times d, which is self.data, dot pow I x minus 1. So this should be, wait, but this is not, I don't know why I'm making a val. This is storing the gradient. This is a float 64. So this is let local grad and then what's wrong here? Cast it. Okay, so now we cast this. So now all I have to do is times local grad. And I think that's it. I think we've now implemented integer power ops for the most part. The only problem is now, so why did we do that? The reason why we did that, and I'll explain why, it's actually really simple, is because, oh yeah, here, because one thing you do is you can take the absolute value, because, okay, what we're trying to do is we're saying, what is the difference between the actual data set answers and our predicted answers, and that's YP. And typically we discourage wrong, like answers that are wrong by more than linear. So that's why we square. So it's just whatever. And then now I think I have to do dot sum, right? So this is let loss equal this. Dot sum. What? Why is that wrong? Okay, I'm just kind of copying off of last time. I'm not sure about this sum function. I mean, shouldn't this just return a val? Can't I just do that? Oh yeah. I think I probably have to do an impulse sum or something. I'm not really positive about that. So let's just get rid of this. The other way that I could do this, I think, is we do y's.iter.zip ypred dot fold. The init is going to be a 0. It's going to be a val new 0. And then the f is going to take the sum and then the yi and the ypred I. And the sum, why is the sum a unit type? Because this is erroring, presumably. What? Expected unit? I think that's just not actually an issue. So we're going to have sum plus, and this is going to be yi minus ypred I, like this, dot pow 2. So that's kind of like the general thing here. Expected. Why is this not a... Oh, because the pred are real vowels. So let's just do that. And then this I don't understand. Y's.iter.zip.fold value new 0. Oh, there we go. Okay, cool. I don't know why. Oh, it was trying to coerce the... Oh, wow. Okay, that's Rust being too smart. All right, so now we got to do this unit, and then presumably this, or reference. Okay, there we go. All right, nice. So this is let loss equal, and now we want to do loss. First, we want to come over here, and we want to move this, comment out this, this, and this, and this, and then we want to make this loss, and here we want loss dot backward. Now we can look at the graph of the loss function. So this is all the forward stuff, and then this is like the loss. Pretty cool. Binary exponential. Binary? What does that even mean? Binary exponentiation. Okay, so now that we have the loss, we want to, and we've backpropagated. We now know the gradient. We now know the gradient of the loss value with respect to the data and all of the weights and biases of the neural network. So one thing that I want to do now is in module, we need a function called parameters. And it's going to take a self, and it's going to return a vec of val. And these are going to be the parameters of the network. Oh, wait. At the trait level. And then I want a function called 0 grad, which is going to take a self. It's going to do nothing except self.parameters.for each p.set_grad 0. Okay, now all of these impls are wrong because they don't have the parameters function. And so this is just going to be self.w.append or .push self.b. Can I do that? What is the right way to do this? Oh no, that's not what we want to do at all. Here's what we're going to do. Let mute params equal self.w.clone. Params.push self.b.clone. Then we return params. And then here, I think I should do self.neurons.flatmap This might be wrong. No, actually flat map is right there. Okay, so here, This is a neuron. And it's going to be neuron.parameters. And that's it. Except I have to collect. And then this is the same thing. Self.layers.parameter. Or wait, self.layers.flatmap parameters. Now that we have this, what I want to do is I actually want to do print line MLP parameters len, and this is just going to be MLP.parameters.len. 41, that's correct. So now we actually get to the optimization part. Now we're actually starting to train the neural network. So we're going to do one step of an optimization thing. So I'm going to define this thing called a learning rate to be 1e minus 2. Or let's do 1. And what I'm going to do is nudge all the parameters in the direction of their gradient. So let's just write it as a dumb loop because I feel like dumb loops are very easy to understand. So for p in MLP.parameters, what we're going to do is p dot let pg equal p dot grad. And then we're going to do p dot set grad of p of, okay, so we have some parameter of the network whose gradient is something. If the gradient is positive and we nudge the data, oh yeah, we're not setting the gradient. We're saying p dot node dot borrow mute dot data is equal to plus equals minus the learning rate, because we're trying to minimize the loss function. And so if the gradient is positive and we nudge the data upward, then the loss will increase. So we want to go in the other direction. Oh man, my shoulder. Is it log n Gagan Madhan? I don't know. Okay. So what we want to do is we actually want to move the in the times PG. I think that that's correct. So if I wanted to do this more functionally, I would do, and let's cancel this because now we're doing, so it's going to be MLP.parameters dot for each, oops, P self dot, or no, P dot node dot borrow mute dot data plus equals minus LR times P dot grad. And I think that that's one step of gradient descent. And so now what we can do is just for 0 in 0 to 100, or for I in 0 to 10, loop over this. So we predict, we compute the loss, we compute the gradient. This can come out here. And then we update the parameters. One thing that we absolutely need to do is after we update, we want to do mlp.zeroGrad. And what we want to do also is print line loss I equals loss dot data equals loss dot data. X's dot clone. Okay, cool. So now the loss is increasing, and is it because why is that? Okay, apparently the bug is an opt.pow. Oh, D is okay. So D equals X. So Z equals X to the N. So Z is self. This is D. So then if I put this here, this is going to be X to the N to the power of this. So this actually needs to be child.data. And there we go. The loss goes from whatever, 7 to 0. So we've successfully trained a neural network from scratch in 2 hours. Okay, so yeah, so that's how to, in 300 lines of code, you really can build something that trains a neural network. And it's like such simple, it's like I love how simple backprop is. I mean, like, the only function I think that really needs to be understood is local backwards. That is the absolute, that and backward maybe, is the crux of neural networks, for sure. But that was fun, man. That was a lot of fun.